Okay, question 6. So this one is the required practical, or one of the required practicals. It's a specific heat capacity required practical. Students investigate the specific heat capacity of different oils. The diagram shows the equipment used. So you will be asked probably something to do with specific heat capacity on your paper. We're being told it's one of the two required practicals that you need to know, IV graphs and specific heat capacity. So you're given a method, so we aren't going to have to use a method, and we're using a joule meter here, which measures energy transfer. So give one variable to the student controlled in the investigation. So controlled means kept the same. So it's going to read the method and find anything that kept the same. So it says put 200 grams of oil in a beaker. Well, already. So the something they've kept the same is the mass of the oil. Record the temperature of the oil, switch on the heater. After 5 minutes, record the temperature. So again, they kept that the same too. They turned the equipment on for 5 minutes. After 5 minutes, record the temperature of the oil and the reading on the joule meter. Repeat steps 1 to 4 with different oils. So you could have anything from mass of the oil, or you could also have the time the equipment was turned on for. Here we have got the student's results. What is the resolution of the thermometer used in the investigation? Resolution, that word there means the lowest number that you can distinguish, the lowest value between. So for instance, if I said, oh, I've got 28.2 and 29.7, I'm going up in point ones. So that could be expected. In this case, I've got 21 and I've got a 68. I could expect something like a 73, but I wouldn't expect 72.9 because that's to another decimal place. So I would only expect to be given numbers that would go up by 1 degree, like differences of 1 degrees. So that's my lowest number, so that we call that our resolution. So our resolution here is 1 degree Celsius. The students calculate the specific heat capacity of the oil. Get the highlighter as 2100 joules per kilogram degree Celsius, or 2100. The correct value for the specific heat capacity of oil is 1630, so 1630 joules per kilogram degree Celsius. So they've got a value that's much higher. Calculate the percentage difference, right? This one here is not going to be on your formula sheet. This is just something you need to know. So first off, the word difference is, let's just find the difference. So what we do is we're going to do 2100 minus 1630, which is going to give us our difference between our numbers. So again, calculator, no matter if you think you can do it in your head, get the calculator. 2100 minus 1630, which is 470. 470. So we've got a difference of 470. Now, percentage is, like if you got an exam and you got, so the exam was out of 100 marks and you got 50 out of 100, then all you would do is I got 50%. So what you do is, to get a percentage, you take the original value that you could have got and divide it by the value that you did actually get. Well, the way around, you take the value you got and you divide it by what you could have got. So for instance, if I got 50 marks out of 100, I get 0.5 times that by 100, which 0.5 times that by 100, which gives me 50%. If I got 70 marks out of 100, I'm going to get 70%, so I'll do 70 divided by what I could have got, 0.7 times that by 100 is 70%. So I'm going to do the same thing here. So I got 470 difference, and I could have got 2100. So 470, and I could have got 2100. So that is a difference of 0.223. So what we do is we times that by 100, So equals times by 100, 22.38. So we got equals 22.38. We don't need to be that specific with percentages, so we can just give it to, the nearest whole number. Nearest whole number, the 3 does not round it up, so we can leave it as 22%. You could have divided it by the other one as well. You could have done 470 divided by 1630. And if you'd have done that, you'd have got 28.8. Okay. So there's two improvements the students can make to obtain a more accurate value for specific heat capacity. Let's have a look at their equipment setup here. So the first thing is, with the specific heat capacity required practical, is that when you put energy in to our joule meter, the joule meter measures that. That's measuring how much energy is put into this heater. And then we're then using the heater to put energy into the oil. We're then, seeing how much temperature increases that heater cause in the oil. But what we can see here, I'll use a red pen, is that not all of that heater is in the oil. So that's something they could so you could get a heater that is smaller and and fully submerges in the oil. So they could do that. The other thing is, I'll use green for this one, is a lot of the heat is going to be given out. So they're going to be heating up that oil, but whilst the experiment's happening, the oil is going to be heating up the side of the beaker, and then the beaker is just going to be giving out the heat into the surroundings. So what they could do in order to reduce that is they could put something around here and even a lid on it, like this is insulation, to stop that heat going out so much into the surroundings. So they could insulate or a lid. So our two improvements, we could say insulate or put a lid on the beaker. Right, we can't say insulate and then in front of a mark put a lid on because that's both to do with insulation. The second mark we can say fully submerge the heater in the oil. We do a practical in the lab where we do this specific capacity and we use blocks of metal, and often when the metal the heater sticks out at the top of the metal, and again it isn't fully submerged, it's the same answer there. So if you had your block of metal here and your heater was like placed in it like that, again the heat here is going out into the surroundings, not into the metal. So it's the same idea. Okay, a company is considering what metal to use to make saucepans. So this is applying it to the real world. Use the data about, they use data about the costs of each metal and the specific heat capacity of the metal. Suggest two other properties the company needs to consider when deciding which metal to use. So we can't talk about cost of the metal, and we cannot talk about specific heat capacity. So we've got to think, what do we want a pan to do? So when we get a pan, and we put it on top of a hob, like this, and the heat transfers up, what do we want that pan to actually do? Well, we want it to heat up quickly, so we want it to, conduct heat well. So we can add that as an answer. So how well it conducts heat. So the better conductor, the better. If you're cooking food as well, you don't want it to be toxic, do you? You don't want to have lead as your metal. Because if you had a lead pan, anything you cooked in it would be toxic and would make you very ill. We'd also want a pan that wasn't too heavy. Because if it was really heavy, or you have a large mass, then you wouldn't be able to move it around. You'd be able to flip a pancake in a heavy pan, so that would be no good. So another thing as well is if you wash it, you wouldn't want it to get rusty all the time. So we don't want it to corrode. If you think about your alkali metals, those group one metals, if you put them in water, they react. We wouldn't want that to happen. We don't want to put water in our pan and the pan to set on fire, so that would be rubbish. So any of those things. So I'm just going to go with the easy one. So I'm going to go with the mass of the metal. Yeah, we don't want massively heavy pans. All right, that's the end of that question.